Continuing on with class 24, we want to introduce the idea of system characteristics and the pump selection. So we were dealing with centrifugal pump and pump curves, and now let's see how they're going to interact with our system design. So the curve that we developed, that we've previously developed, we could use to find an operating point. So you could see, as drawn on here, that we have a system curve right here, and here is the head curve, and where they intersect right there, that's where we're going to predict the operating point right here. So we're saying we're going to predict with this particular pump that we're going to get 1,600 gallons per minute of flow, and that we're going to have an efficiency of 84%. And that the head that's going to be produced is something right around 65 feet. I guess they found it to be 66.5. You could also, from this, determine what the net positive suction head required is going to be. So if there's like an elevation change, that's going to like shift the curve upwards, right? That usually doesn't necessarily going to change. I don't know, is somebody going to move the tank? But I guess they could. It could be like connected to a hose or something. If the maybe the amount of head losses increase, the curve could move over this way right here. But if you were to change the diameter, the curve moves that way right there, the diameter of the pipe. So, actually, this direction right here, we might be able to close a valve to create that kind of motion. Well, we can determine all these things using the Excel spreadsheet that we developed. I guess this was an extra piece of information right here. Sometimes people also might want to know if you had two pumps in series, what the effect would be. You can move the operating point from here to here, or if you had two in parallel, you can move the operating point from here to right there. Right, so there's a difference in the series and parallel operation right here. So here's what we're going to do for this example: is we're going to use our spreadsheet from class 23 with the system from class 23, and then the pump curve that we just used during this class, and try to figure out the operating point, and then maybe modify it to find what would be required to maybe make it a more efficient system, or if we might have some desired pressure or excuse me, flow rate, or a particular pressure for a flow rate. Any of those things. So here was the system, just to remind you that we moved between 60 psi inlet tank here and 120 psi outlet tank, pressurized tank right there, using a centrifugal pump. And we had these drops moving along there. So yeah, we could discard all of that. So here is here is our spreadsheet, and I'm going to modify it now. So I have it set up so where I just have this input of 48 gallons per minute. This one actually should be blank right now, this little liquid. But I'm going to modify it to, for my purposes, I'm going to go ahead and just copy this cell, these cells down to there. I'm going to take the color off of this one because it's no longer there. And I'm going to set this one equal to 0. Boom. You'll see that goes divided by 0 right in there. So we're just going to go ahead and say we could leave it there. Like, actually, it's not hurting anybody to be right in there. So right here for this cell, I'm going to say equals. Whoops. I decided to make this a larger number, so I want 640 in there. And I'm going to make this in increments of 5% of this flow range. So I'm going to go equals the cell just before it plus 0.05 times this cell, and then I'm going to hit a F4 button, and so it's going to be just a 5% of that right there. Now, if I were to drag this down, I don't know how far I have to drag it. Not too far. This is 608. Boom. Okay, so 640. There you go. Only needed to go that far. So what's nice about this is now, in doing it this way, is now I could just change this range and it'll change all these. What I want to use this for is to make a curve, and I want it to be matching the pump curve. So let me go back into my pump curve and come back up to here, and I'm just going to copy this into place and make it something that's a little, I guess I can zoom out. I'm at 120. There you go. I can zoom out. There you go. That's not too bad. So I'm going to make a curve and I'm going to superimpose it on top of this. And this is in gallons per minute. Yep, US gallons per minute. And this is in feet. So I'm going to take this column and I'm going to hold down, I think, Control, and this column right there. And I'm going to insert a graph. And this time I'm not going to use data points, just going to use a curve. And that doesn't look correct. Why not? All right, so give me a second here. Let me pause and figure out what I did wrong. Okay, I figured out what I did wrong. All right, so I had accidentally already deleted out this head loss thing. So if I had done it correctly, this head loss would have had the equation right in there. And so I'm going to copy that over. So yours would have already had that in there. You can see that it's going to be divided by 0. But that's only because I made this guy 0 over here. So when we move him into place, yeah. So I can just go ahead and delete that one right there. Make that head loss 0. And so that now we can see that we're going to have, what the correct curve is going to look like. I don't have enough time to go back and re-record this, so I'm going to go ahead and leave it in there. So we could fix the title here. Get rid of that title. Change the background. So I'm going to format the plot area. I'll get rid of the fill. Boom. No, it should have been this one. Change the fill. No fill there. Oh, no, solid fill. No fill. There you go. All right, so it's hard to see right in there, but that's now I've removed the fill. I'm also going to get rid of the border right there. No, I don't like the border. So what I want to do now is to match the. Let's see, hard to see. I'll draw it down here. I'm going to match the vertical axis denominations here. I think I'm going to go up to. I'm going to go from 0 to 300. I think that'll be wise. 0 to 300. So I'll try to capture. There you go. And go to axis options and changes from 0 to 300. And it looks like it's at increments of 50. It's already doing it at 50, but I'll make sure it does. I'm going to change the number and get rid of that extra decimal place that's not needed. Let's see, for the x-axis, it does a weird thing where it goes to 640, but it's counting by 80s. So let's see, we'll go ahead and do that too. So we'll go to 640. I think it's going to want me to, I need to put in 0 for the minimum, and then count it by 80s. And good, we got it. Okay, so I can superimpose this, get the zeros to line up. I'll move this over here to the 80. Oh, okay, I'm grabbing the wrong tab there. I got to grab that tab, yeah, or that little guy right here. Boom, I got him to match up. Here's the outside one, move him up, and then grab the inside one. I'm gonna move him down to 300, and there you go. Boom. So right about there. Oh, and I had accidentally, I'll learn this for the class. This should have been, if we're going back to this original problem, this was 2 inches everywhere, which will look like, I had already changed it to the 3.5, so spoiler alert, there you go. So this is what the system would look like and what we would predict with our 7.5-inch diameter pump is that we would predict something along the lines of a flow, well, I don't know, somewhere between 120, which is like right there, right? So what is half of, yeah, so the midway point between 80 and 160 is 120. So I'm going to say it's probably somewhere, like somewhere in the 140 range, 140 gallons per minute. And so that would be the answer to the problem, or to what I had the example statement right here. It says okay, so determine the operating point. Right, so if I could mark up on this, and I don't know, maybe it will let me mark up on this. I don't know, maybe, yeah, could make a little point like right there. Sure, onto that would be what I would assume would be my operating point, and actually it's probably pretty close to that 140, isn't it? Yeah, 120. I think that's 120, like right in there. So let's modify it. They asked us to modify this I did, so that the pump is used most efficiently, right? And so what we could do, and even though this isn't the exact correct inside diameter as we've learned, right? We could, let's just go to what happens when we have 2.5, right? So you can see where we've done. We've shifted we've shifted the curve over. We could increase that to 3 inches, and that's better. And then 3.5, and that's what I thought. Look, you can see that it's pretty efficient right here. We're talking about like right there now, in that location. What about 4 inches? How does 4 inches do? It's on. We kind of overshot it, right? This is probably the location of the best efficiency that we're going to get. So I think 3.5 is a pretty good size, but it also depends on what we want for a flow rate, right? So this is the flow rate that we would be predicting as part of this. So another aspect that we might ask as part of a problem like this is, well, what if we had 4 inches and we wanted to increase, say we put a valve in that we could control what the K is. So we could just start trying to change this. Let's say that we increment by tens. Boom. We could increase and move this thing up, go by 20. Right there, we could start to use a regulating valve. That's what we're essentially doing by changing this K value. Right here, we're putting a restriction in the system. It's not a great way to regulate things, but we could also, in reality, a lot of times we'll use a bypass and to recirculate. But we could change by just turning a valve, and that's what we were doing by adding this K. So this is the system and pump matching procedure, and with this we can become pump system and system designers.